So the pizzas are here. Thomas is the person standing between us and pizzas. So we bring or so it's up to you how much time we will let go to make it full. But otherwise, that was really great talk, and thanks for like pitching in and then putting it. We did not expect so many submissions, and then we were really glad. I think Thomas is going to talk about small models and yeah.
So yeah, much more simple than Llama 3, definitely, so I'll try to put it in 5 minutes. So where I work in Chimney. We're a big data provider of property data for United Kingdom, so we need to process a lot of postal addresses to join different data sets, and these data sets, these addresses have different formats depending on the origin. So we have always the problem of dividing the address into its components to be able to join on the different parts. And we were so far using a library called libpostal that is actually quite good, but it's for the whole world, and we are only focusing United Kingdom. So when you put an address of United Kingdom, many times it has some special things only of UK that libpostal cannot get. So we said, okay, maybe we can make a more specialized model just for UK addresses. So what we did is we trained a quite small model, just 50 million parameters transformer model for name entity recognition, because basically we want to recognize what is the street, what is the apartment floor, what is the postcode, what is the city. So we use a data set called address base. It has 30 million properties, basically all the properties in the UK, all the addresses, and converted to the Conenel 2003 format, which is gives a tag to each word. So this is the beginning of building name, and this it means is inside the previous one. So these two are actually together, and the same for all the others. So it's like where the token begins and whatever else is part of it. That's how it gets tagged. So to train it, we didn't go deep like Nishan to the math. We just use Hugging Face transformers. So something very important is to train the tokenizer from scratch. That's what's going to give a big performance boost when you can train on a vocabulary exactly for your problem. So in our case, we got the 30 million addresses, we trained the tokenizer on those, and we just set a vocabulary size of 10,000 because the entropy on addresses is much less than on English language or than on language in general. This really reduced the model size and still was able to perform really well. So this we train it on the 30 million. And here we can see it's tokenized. We use the byte pair level tokenizer. So it tokenizes the spaces also. This G is because it catches space. Then we load the data set in the Conenel format, 30 million addresses, but then we split it as usual. We only take 5 million. We saw that was enough to not overfit the model. So now we have it divided and we have all the tags there. Now we can see each one is tagged properly from the dataset. We love the tokenizer. The tokenizer was quite fast to train. It took only 15 minutes for the 30 million addresses because it's the fast version of the Hugging Face tokenizer is used by Torch, and it's really fast. By the way, all this was training in this laptop. It has a 3070 GTX. Yeah, then we need to do some adjustments to match the words, because when we tokenize, many words get split, and we still need to assign the same tag. So all this that is doing is adjusting the tokens to the correct tag, even when it has been split. And then about the model architecture, yeah, this we load the tokenizer. This the collator. This is to make, for training, it's better to have the same size of inputs for every batch. So we pad, if some addresses are shorter, some are longer, we pad them so all of them in the same batch have the same size. That improves performance and training quite a lot. This is to compute the metrics. And yeah, so here is the model configuration. So we use Roberta, but very much reduced. The original Roberta used 52,000 vocabulary size. Now, as we said, we use 10,000 only. Only 514 position embeddings is actually even too much for addresses, but we didn't want to play it too small. 8 attention heads and 6 hidden layers. So it's a very small model compared to the full Roberta original one. And 25 labels, which is all the different tags we have for the addresses. So we trained this for 400,000 steps, 20,000 in 3 epochs. This took 7 hours to train with the 5 million addresses. It's already on over here. It starts to go down the accuracy, so more or less around here it was fine. And now we can see if we load the model. It has 50 million parameters, 50,600,000. Now we can load the model and parse, for example, this address. We pass it directly. We need to pass it uppercase with no commas, nothing. And it tells us this is the sub-building name, the building name, number, street, blah, blah, blah. And we compare it to Lead Postal. Lead Postal, for example, is having problems with this address. This one, these high cedars, instead of knowing that is the building name, it thinks it's the road 2 times. So already, this small model turned out to be 200 megabytes only. So very, very light. Lead Postal takes 2.5 gigabytes in memory. It's already handling many edge cases that Lead Postal couldn't, just because it's for the whole world. And about speed, it's slower than Lead Postal, to be honest, on single inputs. But when you do batching, we can reach the speed of Lead Postal. And because the model is so small, we can load it many times. Like we can load it 10 times, where Lead Postal will just 1 instance. Yeah, that's it. So this is why I think it's good to start with big models, but then when you have a use case that you think you can narrow down, it's worth thinking about how can I make a specialized model for this use case that will take much less resources to run and might even be more performant than the large model. And I think we're starting to see that there is some generalist models going huge, and then more specialized models going smaller, trying to even make it work in a phone, for example, like the Microsoft 5.3, the tiny one can run in a phone. It's like 14 billion parameters and it can run. So I think that's the balance too. Like, I think to do explorations, it's good to go with large models. Then when you have a narrow idea of what you want, is the time to do something specialized for what you want to do. And yeah, that's it. It's our time. Yeah. Now you are keeping the people from the pizza.
One short question. Did you compare to the baseline of just writing a prompt, maybe a few short examples, and then just asking a general model to do the same job?
Yeah, it could do it, but slower and much more expensive. We need to run this on hundreds of millions of addresses.
Okay.
So it doesn't scale, you know. We do batch processing of the whole United Kingdom for more than 100 different data sets. So it needs to be really cheap.
Okay.
Yeah.
Good.
Okay. Thank you, everyone.